Today we're going to demonstrate the properties of how to size a control transformer and the importance related to it. Here I've got two control transformers, one rated at 50 VA and one at 25 VA. Now, of course, inside of the enclosure, it doesn't mean much, but let me turn these transformers onto their side so we can do an actual comparison. We can see the differences in between both transformers. It's that the core of each of these transformers is significantly different. The smaller VA transformer at 25 VA, we can see that the core is roughly half as wide. This relates to the amount of power output that the transformer can give us in our control circuit. Now, what are some of the problems associated with undersizing a control transformer? When we look at the various relays, and here I've got contactors from the lav volt workstations to try and demonstrate that when we don't size our control transformers accurately, we're going to have problems with our control circuits. Namely, that my relays are not going to energize and pull in because of the fact that the relays are basically air core inductors at the point in time when we will activate or energize our control circuit. And due to that fact, they require an awful lot of apparent power on startup. But once the armatures have pulled in and have closed, the coils have now energized, the armatures have changed state, the holding power is going to be drastically less. Now, I'm going to proceed now before proceeding to our demonstration where we're going to wire up a circuit, let's do a little bit of math and look at what the math is going to reveal. Inside of these contactors, the company has used what we call Allen Bradley 700 series relay. In the specifications provided to us by the manufacturer, we got the following two pieces of information. We call the inrush VA for this particular relay 138 VA. Now, depending on the manufacturer, inrush VA could also be substituted for another term they call the open VA, meaning that your relay, the coil is at rest, the armature is in the open position. Now, we've got what we call the sealed VA, and that came in at 19 VA. Quite a big contrast in the values, and actually it's about 6 times less. And again, consequently, if this was the open VA, certain manufacturers will describe this as the closed VA, meaning that once the armature has pulled in because the coil of a relay is energized, the magnetic flux has grown exponentially due to the fact that the coil is now an iron core inductor. And as such, it does not require the same value of apparent power to maintain a closed state. Now, when we start talking about 125 VA control transformer, I have more than enough power to energize one of these relays. But accordingly, at 25 VA, for a control transformer, I will not have enough power to have more than one control relay closed at any point in time. So that's what the math is showing us. Let's put that to the test. So here we are. What I've done is I've assembled a series of 4 individual relays. My goal here is we're going to build a simple control circuit with a holding contact, and I'm going to start off with the 25 VA transformer. Now, this transformer has an input of 208 volts and an output or a secondary of 120 for the control circuit. So I'm going to go ahead, wire up for the 208 on the primary, and then we're going to power it up go into my control station, and I'm going to complete the circuit by going to X2. And I'm just going to go and power up my power supply. We now have control power, and I'm going to proceed to energizing the first relay. So here it goes. With a single relay on my control circuit, I depress the start button, and we can see that the armature has actually pulled in. You're not going to pick up that there's any noise whatsoever. Everything is working the way it should. Indeed, when we did the math, we saw that a 25 VA transformer has more than enough power to energize for the inrush current for the relay coil, and it has enough to maintain it. Now I'm going to hit the stop button, and I'm going to add a second relay into this circuit. And it's simply a matter of piggybacking one lead and going to the coil of this second relay. Now let's try this again. Here goes. Let's do that again. Now what you can see is that there is a little bit of travel in between both of the armatures. There's a real audible noise, and the fact is when I release pressure on the start push button, everything is reverting back to its shelf state, which really goes to prove the theory that a 25 VA transformer does not have enough to deliver the inrush current required to get these two relays to change state, much less have enough power to maintain them in that state. Now I could add a third one, and I'm going to get the exact same results. So let's add that third one by piggybacking and adding that third relay. And do it again. Again, you can actually see that with that third relay, the armatures aren't moving at all, and we still get that very audible hum. How do we solve this? Well, the first thing is we actually have to go back and size the control transformer to allow for the amount of inrush power that is required by each of these devices. Now, how do we deal with a control circuit that contains two relays? I'm referencing information I obtained from Eaton as well as from Anlin Bradley or Rockwell Automation in how to properly size a control transformer. I need to take the values, the inrush VA, and I have to multiply it by the number of devices in my circuit. In this case, 138 VA, which is an open value, we're going to multiply that by two relays. And as a result, I'm going to need 276 VA. And now for holding, or the sealed VA, we're going to take the 19, multiply it by the two relays, and that's going to be 38 VA. Now, in the formula provided to us, your total inrush VA is equal to your inrush VA squared plus your sealed VA squared and square root. So we're going to go and input our values, and we're going to proceed to calculating that. In this case, 276 VA squared plus 38 VA squared, 278.60 VA total inrush. Now that I have this value, I just need to consult one of the technical charts provided to us by the control transformer manufacturer to see which one of the control transformers is going to provide us with the appropriate amount of power to meet our needs. Now, I've already done some of this work beforehand, and I know that the 50 VA transformer will be more than adequate for this task. So now that we've done that, let's go back and actually build the circuit and put it to the test. So what we're going to do now is we're going to exchange the 25 VA transformer for the 50 VA transformer right here. And indeed, I've actually taken the opportunity to have all of the 50 VA transformers properly labeled to avoid any mistakes in our labs. So the first thing, I've already taken apart the input power. And so we're going to wire up the secondary. So this is going to the neutral, or X2. Up here, this is going to go to my push button station. And finally, we're going to power things up for 208 volts. Now, you can see that I've got the larger coil, or pardon me, the core. So I genuinely have a 50 VA control transformer in my circuit. So I want to pick up where we left off, and I'm just going to strip out these leads, and we're going to start off again with one relay. So here goes. With a single relay in my control circuit, I'm going to energize the circuit, and you can see the same thing as happened before. The one armature has pulled in, no big noise, everything is working the way it should be. Let's drop that out and add that second relay. And we're going to piggyback onto this one. Now, with two relays in my control circuit, let's energize. Now, this is where things fell apart the last time because of the fact the 25 VA control transformer could not deliver enough apparent power for the inrush for both of my relays. And you can see everything's working just nicely. Now, I haven't done the math, but let's get a little bit crazy. Let's try a third relay. So let's keep adding and see how far we could take this. So we're going to start with 3 relays in our control circuit. And here goes. We can see that each of the individual relays have all changed state. The armatures have traveled and everything is now in a closed state and maintaining it. There's no telltale audible hum, meaning that the transformer is struggling. Everything is as it should be. Now, let's take it further. I've got a 4th relay. Let's try and energize it. So first, for safety's sake, we'll de-energize the control circuit, grab another lead, and we're going to add a 4th relay to the mix. And again, here it goes. 1, 2, 3, and 4. They're all working, but there's a little bit more noise or humming coming from the relays. Now, while the transformer is providing us with enough power, it could be that we're actually drawing a little bit more current than the transformer was ever designed to deliver. And this is where it brings up that last note. When we are trying to draw more current from the transformer than it was designed to, according to your manufacturer, I'm not saying the transformer can't do it, but what's happening though is that you're going to shorten the life cycle of this piece of equipment. If the transformer is humming, it means that it is starting to struggle to provide you with all that apparent power, meaning true power, reactive power, to feed all of your devices. And that's one of the biggest things that we have to look at. It's our responsibility as electrical workers to properly size our equipment so that we can ensure the longevity of the equipment that we're putting together.